So let's take a look at the difference between linear, exponential, and logarithmic growth, because we have seen all of these three types of graphs so far. So here is an example of a linear growth where something is increasing at a steady constant rate. Exponential growth here is something that starts growing slowly, but then it grows more and more and more as time goes by. So think about like the COVID numbers, after Thanksgiving or Christmas holidays, there's a surge after those peak times. And then the logarithmic growth, it grows, and then as time passes, it grows and slows down. So think about like maybe your height as, babies grow super, super fast. And then eventually, right, we all slow down in terms of growth. So here's linear, exponential, and logarithmic growth. Okay, so for the model of exponential growth or decay, we have A equals A naught or A initial. This little zero indicates the initial value of A at the initial time when time is 0. E and then KTE is a number that's like pi, that with pi we all know it's 3.14. E is around 2.718. It's a number that occurs, it's a base E that we use a lot in exponential growth and decay models. So there's E. A here is the amount at time t. So this right here is the final amount when we're interested in that time t. Here's the initial. And when k, this is the rate of growth or rate of decay. Whether we know it's a growth model, so growth model tends to increase, I think population increases, or decay model when something falls, decays. So if k is greater than 0, if k is positive, we know this is a growth model. If k is less than 0, if k is negative, we know this is a decay model. All right, so I wanted to take a look at Georgia's population with you all from 1740 all the way to 2020 recently. So we know every 10 years the census goes out and tries to count all the people in Georgia, and that's to make sure that we spread out the resources correctly, make sure that we have enough seats in the House. And so here is Georgia's population growth over time, and you did see a growth, and it's not, it's not a perfect exponential growth model. Sometimes you do see a dip, but overall it does follow an exponential trend upwards, like a curvy. It's not a linear model. A linear would be like a straight growth, but it does fit like a general exponential curve. Not perfectly, of course, there's no, in the world, there's no perfect exponential model, but you can see that it is growing over time exponentially. So here, let's look at the population of Georgia. Back in 2010, the population of Georgia was 9.7 million, and it grew to 10.7 million in 2020. Let's calculate the projected growth rate of Georgia and round to 4 decimal places. So for this, I think I'm going to need enough more room, so I'm going to push that down. For this here, what we need to do is we have to calculate K, the growth rate. So remember back on that slide where I shared with you the growth rate models, A equals A initial or A naught, E, K to the T power. And we're trying to calculate K. So when it says growth rate, we're trying to find what is K. So to find K, then we would need all the other variables. We would need to know what A is. We would need to know what A initial is. And we also need to know T. And we are given that in the problem. So it's A is the most recent population number, which is 10.7 million. I'm just going to write 10.7, and because we know that's expressed in millions. The initial, back when it started, 2010, is 9.7 million. E, and then K is what we're trying to find. T is the amount of time that passed from 2010 to 2020. So T is difference of 10 years. So I'm going to write 10. Usually, though, we write numbers between the variables. I'm going to just write 10K. Now we're trying to solve for K, and we've done exponential equations where we have to get the base isolated. So there's this 9.7 in the way. So we first have to divide both sides by 9.7 to cancel that out. We're trying to get E by itself. And then we have 10.7 over 9.7 equals E to the 10K. Now at this point, we're going to take the ln of both sides. And what that does, remember ln of E is just 1, so I can just ignore that. And then we can write ln 10.7 of 9.7 equals 10K, because ln of E is just 1. And now, actually, that should be 10 times K, not 10 to the K. Now to get K by itself, we can divide both sides by 10. And K is going to be ln of 10.7. So let's put that in the calculator. 10.7 divided by 9.7 all over 10. So let's round to 4 decimal places. We have 0.0098. That's our growth rate. So it says, what is the exponential growth function that models the data? So it's going to be A equals, the A initial is going to be 9.7 with E 0.0098 T. This is T is years after 2010, because we're using our initial value starting 2010 at 9.7 million. All right, so there's number 1. Let's look at number 2. So based on the previous calculations, we got the exponential growth model for our state. A equals 9.7 E to the 0.0098 T, where T is years after 2010. Let's project the population of Georgia in 2030. So this is important. The agencies want to know what the projected population model may be based on, whether they want to build more schools, do they need to build more housing, do they need to build more roads. So this is important just to get all of that, the projection, so that they have everything they need when the population growth does happen. So here we have A equals, so we're looking at A, the final amount at 2030. So that means we need to know T. Well, T is 2030 minus 2010. That's going to be 20 years. So in here, 9.7E, 0.0098. I'm going to multiply by 20. So we get 9.7 E 0.0098 times 20. And based on our model, it's going to be 11 point, let's just round to 1 decimal place, million people in 2030. Let's calculate when will it reach 15 million. So to do that, it's asking for T. We're trying to find when does that happen? So we have A, our final amount that we're trying to see when that happens is 15. The initial is 9.7, E 0.0098. We don't know T this time. So again, trying to isolate E first, get that 9.7 out of the way. And so then we have 15 over 9.7 equals E to 0.0098T. At this point, to cancel e and make the power come down, we do ln of both sides. So ln of e is 1, so I'm canceling that. We have ln of 15 over 9.7 equals 0. Oops, I think I need more room, so I'm going to put that over on the side more, 0.0098 t. The last bit is to cancel 0.0098 to isolate t. So we have t equals ln of 15 over 9.7, so calculator time. 9.7 divided by 0.0098, giving us 44.48-ish. So that is the number of years it'll take after 2010. So I'm going to add that to 2010. So we have like 2054-ish, 2055. I think I would take both, because if you add that right to 2010, you get 2054.48. If you had put 2055, I think that would be fine too.